Cement is a manufactured inorganic material produced by clinker formation in a rotary kiln and subsequent grinding with gypsum and/or supplementary materials, which develops mechanical strength, durability, and volume stability through controlled hydration, in compliance with standards such as ASTM International C150 and British Standards Institution in 197. Every bridge you design, every tower you raise, begins right here inside a cement plant where chemistry, heat, and precision decide structural fate. Miss one parameter and your concrete fail before it even sets. Because cement is not just a material, it is the hidden architecture of modern life. And this is how it is made. Have you ever wondered that how ordinary limestone is transformed into the cement that builds skyscrapers, bridges, and cities? Today we will take you inside a modern cement factory to explore the complete manufacturing process. Let's begin from the very first step and see how raw materials are extracted, processed, and transformed into high-quality cement. Cement manufacturing begins at the quarry, where limestone deposits rich in calcium carbonate are carefully selected to establish stable clinker chemistry. Engineers analyze limestone, clay, silica, and iron content using geological surveys and X-ray fluorescence systems to maintain precise raw material composition. High calcium availability is essential for controlling the lime saturation factor, which governs clinker quality and kiln stability. Even minor chemical variations can increase fuel consumption, disrupt clinker formation, and reduce cement strength. Controlled blasting and selective mining minimize contamination from low-grade rock while maintaining consistent feed chemistry. Modern computerized mine planning ensures long-term chemical uniformity throughout extraction operations. Stable kiln performance, therefore, begins with precise control of geology at the source. Cement quality is fundamentally engineered before raw materials even enter the plant. After extraction, raw materials are transported through automated haulage and feed systems where accurate proportioning becomes critical for clinker stability. The raw mix typically contains about 78% limestone, 20% clay, and corrective iron-bearing additives to balance silica, alumina, and ferric oxide levels. Automated weigh feeders and conveyor systems maintain flow variations within extremely tight tolerances. Any inconsistency introduced here directly affects kiln chemistry several hours later due to the continuous process cycle. Stable feed ratios are essential for maintaining flame stability, fuel efficiency, clinker mineralogy, and final cement strength. Real-time monitoring systems continuously track material density, belt loading, and chemical composition. Transportation in cement plants therefore functions as integrated process engineering rather than simple logistics. Precise feed control protects downstream thermal and chemical stability. The crushing stage reduces large quarry rock into uniformly sized particles suitable for efficient grinding and thermal processing. Primary jaw crushers perform initial fragmentation, while secondary hammer or impact crushers refine the material to below approximately 25 millimeters. Uniform particle size improves grinding efficiency, reduces vibration, and lowers electrical power consumption within the milling circuit. Oversized fragments can destabilize separator performance and reduce raw mill productivity. Modern crushing systems integrate vibration monitoring, automated gap adjustment, dust suppression, and predictive maintenance technologies. Consistent feed size ensures smoother downstream processing and improved raw meal homogenization. Crushing is therefore not simply fragmentation, but preparation for precise chemical engineering. Efficient crushing directly improves plant energy performance and operational reliability. Natural quarry materials contain unavoidable variations in chemical composition that must be stabilized before grinding. Pre-blending stockpiles use stacker reclaimer systems to deposit limestone and clay in layered formations that homogenize material chemistry. Controlled stacking and reclaiming can reduce chemical fluctuations from nearly plus minus 8% to approximately plus minus 1%. Stable raw feed chemistry prevents kiln instability, poor clinker formation, and excessive fuel consumption. Without pre-blending, operators would constantly struggle to correct fluctuating free lime levels and unstable burning conditions. Modern plants rely on predictive stabilization rather than reactive process correction. The pre-blending yard therefore acts as the first major chemical buffer within the cement plant. Consistent raw feed significantly improves kiln efficiency, clinker quality, and refractory life. Inside the raw mill, crushed materials are simultaneously dried, ground, and separated into an extremely fine powder known as raw meal. Vertical roller mills and ball mills use hot kiln gases to remove moisture while achieving the required particle fineness. The raw mix is engineered to precise chemical targets containing controlled levels of calcium oxide, silica, alumina, and iron oxide. Fine particle distribution is essential for complete calcination and efficient clinker formation inside the kiln. Excessively coarse particles create incomplete reactions, increase free lime content, and reduce cement quality. Automated control systems continuously monitor separator efficiency, grinding pressure, power consumption, and product fineness. This process transforms natural minerals into a thermochemically optimized kiln feed. Raw milling therefore plays a critical role in energy efficiency and clinker reactivity. After grinding, raw meal enters homogenization silos where compressed air blending systems continuously circulate and stabilize the powder. Fluidization technology ensures uniform distribution of chemical components throughout the silo volume. This process reduces raw meal variation to below approximately plus minus 0.5%, creating highly stable kiln feed conditions. Stable chemistry protects the kiln burning zone from thermal fluctuations and refractory stress. Even small feed variations can reduce fuel efficiency and destabilize clinker formation in large-scale plants. Homogenization silos therefore function as chemical insurance systems for downstream thermal processing. Modern silos are engineered for continuous blending, controlled discharge, and stable process flow. Uniform kiln feed significantly improves clinker consistency and operational reliability. The suspension preheater tower maximizes heat recovery before raw meal enters the rotary kiln. Hot exhaust gases flow upward through multiple cyclone stages while raw meal descends in counterflow motion, creating highly efficient heat transfer. During this stage, calcination begins as calcium carbonate decomposes into calcium oxide and carbon dioxide. Up to 40% of calcination may occur inside the preheater, significantly reducing kiln fuel demand. Efficient preheating lowers operating costs, improves thermal efficiency, and reduces carbon emissions. Multi-stage cyclone systems are among the most important energy-saving technologies in modern cement plants. Preheaters therefore play a central role in sustainable clinker production. The rotary kiln is the core chemical reactor where clinker minerals are formed under extreme thermal conditions approaching 1450 centigrade. Inside the rotating steel shell, calcined raw meal undergoes clinkerization to produce the compounds responsible for cement strength. The most important clinker phases are tricalcium silicate and dicalcium silicate. These minerals govern early strength development, durability, and long-term concrete performance. Engineers precisely control flame temperature, oxygen supply, kiln rotation speed, and residence time to stabilize mineral formation. Excessive lime saturation factor can leave unreacted free lime, reducing cement quality and durability. The rotary kiln therefore operates as a highly controlled thermochemical reactor rather than a conventional furnace. Inside the burning zone, complex reactions transform raw meal into hard clinker nodules composed of carefully engineered crystalline phases. Alite is the dominant clinker mineral and typically represents 50 to 60% of ordinary Portland cement clinker. Belite contributes to long-term strength development and lower heat generation. Additional phases such as tricalcium aluminate and tetracalcium aluminoferrite influence setting behavior and sulfate resistance. Final clinker mineralogy directly controls compressive strength, shrinkage, durability, and hydration heat. Engineers carefully balance phase composition according to structural performance requirements. At this stage, cement properties are fundamentally engineered at the microscopic mineral level. Fresh clinker exits the rotary kiln at temperatures above 1400 centigrade and must be rapidly cooled to preserve mineral quality. Great coolers use controlled high-volume airflow to stabilize clinker crystal structure and prevent unwanted secondary reactions. Rapid cooling locks desirable alite phases into stable forms before decomposition can occur. Slow cooling reduces early strength development by converting reactive minerals into less active phases. Clinker cooling also improves grindability and hydration reactivity during final cement production. Modern coolers recover large amounts of thermal energy and redirect it into the kiln and preheater system. This significantly improves overall plant thermal efficiency and fuel economy. Clinker cooling is therefore a critical thermodynamic process affecting both energy performance and cement quality. After cooling, clinker is stored under carefully controlled conditions to preserve chemical stability before grinding. Moisture exposure must be minimized because premature hydration reduces grinding efficiency and cement reactivity. Enclosed silos, domes, and covered stockpiles protect clinker from rain, humidity, and contamination. Surface hydration can form unstable compounds that increase grinding power demand and reduce strength development. Storage systems also prevent segregation between fine and coarse clinker fractions. Modern clinker storage therefore functions as both a quality protection system and a production buffer. Stable storage conditions ensure consistent downstream grinding performance. Protecting clinker quality is essential for maintaining final cement reliability. Cement grinding is one of the most energy-intensive stages in cement manufacturing. Clinker is finely ground together with approximately 3 to 5% gypsum to regulate setting behavior and prevent flash setting during hydration. Grinding fineness directly controls hydration rate, strength development, workability, and setting characteristics. Fine particles accelerate early strength gain, while coarser fractions contribute to long-term performance. Modern grinding systems use vertical roller mills, closed-circuit ball mills, and high-efficiency separators to optimize particle distribution. Engineers continuously monitor blade fineness, residue values, grinding temperature, and separator efficiency. This stage transforms clinker into the final engineered cement product used in concrete construction. Modern cement plants incorporate supplementary cementitious materials such as fly ash, slag, silica fume, and limestone fillers to improve performance and sustainability. Fly ash replacement may reach up to 35% in blended cements, reducing heat of hydration and improving sulfate resistance. Pozzolanic reactions between silica-rich additives and calcium hydroxide generate additional calcium silicate hydrate gel. This reaction improves concrete density, reduces permeability, and enhances long-term durability. Supplementary cementitious materials also reduce clinker consumption and lower carbon emissions from cement production. Engineers carefully optimize additive proportions according to strength, workability, thermal behavior, and durability requirements. Additives therefore allow modern cement to be customized for specialized engineering applications. Finished cement is stored inside silos where moisture protection and flow control become critical. Cement is highly sensitive to humidity and compaction due to its extremely fine particle size. Aeration systems inject controlled airflow into the silo base to prevent bridging, lump formation, and material compaction. Poor aeration can cause false setting, reducing concrete workability during mixing operations. Modern silos integrate pressure sensors, level monitoring systems, controlled discharge equipment, and dust filtration technology. Stable storage conditions preserve cement reactivity and maintain smooth dispatch operations. Cement silo management therefore extends beyond storage into active material preservation engineering. Reliable silo performance is essential for maintaining cement quality before distribution. The packing plant represents the final precision control stage before cement enters the construction market. Automated packing machines fill bags under tightly controlled weight tolerances to ensure regulatory compliance and commercial accuracy. Small filling errors can create major financial losses or customer disputes at industrial production scales. Electronic load cells, barcode systems, robotic palletizers, and automated weighing controls maintain high operational precision. Dust extraction systems protect workers while minimizing product loss and environmental emissions. Real-time monitoring systems continuously track bagging performance and production efficiency. The packing plant integrates process engineering, industrial automation, and logistics management into one coordinated operation. Accurate dispatch control protects both product quality and commercial reliability. Bulk loading systems support large-scale cement distribution for ready-mix plants and major infrastructure projects. Cement is transferred directly into tanker trucks through automated loading spouts operating under controlled flow conditions. Airtight transfer systems are essential because cement is highly sensitive to moisture contamination during transport. Dust suppression systems minimize airborne particle emissions and improve environmental safety. Modern terminals integrate weighing systems, tanker identification technology, automated dispatch controls, and logistics monitoring software. Bulk transport reduces packaging costs, handling requirements, and material waste compared to bagged cement. Efficient loading systems are essential for continuous concrete production at industrial scales. Bulk logistics therefore form a critical link in the global cement supply chain. Before dispatch, cement undergoes rigorous laboratory testing to ensure compliance with international engineering standards. Laboratories evaluate clinker chemistry, cement fineness, setting time, soundness, and compressive strength development. Compression tests on mortar or concrete cubes are conducted at 3, 7, and 28 days to verify structural performance. Additional testing measures sulfate content, hydration heat, blane fineness, and residue values under standardized conditions. Advanced technologies such as X-ray fluorescence spectroscopy and X-ray diffraction analysis provide continuous chemical verification. Automated sample preparation systems improve testing accuracy and process reliability. Standards established by organizations such as ASTM International and the British Standards Institution define acceptance criteria. Quality control laboratories therefore function as the final engineering barrier protecting structural safety. Modern cement plants operate under strict environmental systems designed to reduce emissions and improve sustainability. Crushing, grinding, kiln operation, and material handling generate significant quantities of fine particulate matter. High-efficiency bag filters and electrostatic precipitators remove airborne particles before atmospheric discharge. Electrostatic systems electrically charge dust particles for separation, while bag filters physically capture ultrafine material with extremely high efficiency. Continuous monitoring systems track particulate emissions, nitrogen oxides, sulfur oxides, and carbon dioxide levels in real time. Waste heat recovery systems and alternative fuels further improve plant energy efficiency and reduce carbon intensity. Environmental engineering has therefore become an integral part of modern cement manufacturing. Sustainable operation is now essential for technical, economic, and regulatory viability. The final purpose of cement manufacturing is the creation of durable concrete structures where every production parameter directly affects long-term performance. Clinker chemistry, grinding fineness, moisture control, and thermal stability collectively determine concrete strength, workability, and durability. This engineered material ultimately supports bridges, dams, highways, skyscrapers, and reinforced concrete systems exposed to harsh environmental conditions. From quarry extraction to final dispatch, cement manufacturing integrates geology, chemistry, and process engineering to ensure structural safety and infrastructure reliability.